there's a problem. All right, I'm live. Can you see it?
It's loading. Oh, yeah, I can.
It's loading now. You can see it. All right. So let's go over a generic question. So I'm going to call my reactant acid. I'm just going to call that R for reactant H, right? Because it has the proton that's being transferred. So this is your proton donor. And the product acid, we'll call that pH, right? Again, that's your proton donor there. So the conjugate base of RH would be R minus, and the conjugate base of pH would be P minus. So the overall reaction could be written as RH, your reactant acid that's donating the proton, plus P minus, right? This is accepting the proton. And then that's in equilibrium with R minus, right? Which is the conjugate base, and pH, which is the conjugate acid. Are you generally able to get that far? Where you're labeling your acid base, your conjugate acid, and your conjugate base correctly?
Yeah.
Okay. So that's kind of the setup. And then there's a bunch of different ways you could possibly approach the problem. But what usually works best for people is to break it up into RH losing a proton separately from the P minus picking up the proton. So you're writing two different equilibria. You're pretending those reactions go one at a time, and there's just a proton floating around somewhere. So then we can cross those two protons off, right? Because it appears on both right and left, and we get the overall balanced equation. Are you generally comfortable with getting that far?
I think so.
And then you know that the overall KEQ is always equal to the product of the reactions that you add together. Right? It's the sum of the reactants for things like free energy and enthalpy and entropy, but it's the product for equilibrium constants. Add reactions, multiply equilibrium constants. So if I know K1 and I know K2, I'll be able to get the overall equilibrium constant. Does that make sense?
Yeah.
Cool. So then the question is, where do these come from? Right? This is a Ka expression. Right? The acid is on the left. And so the equilibrium constant K1 is equal to R minus times H plus over RH. That is a standard acid dissociation constant. K2 is equal to your pH, right, your acid, over H plus times P minus. That's not an acid dissociation constant. That's actually upside down. So that's 1 over the Ka. So K1 is equal to Ka for RH, and K2 is equal to 1 over Ka for pH. Still with me?
I'm confused about how you went from the
How I got the reciprocal?
the 1 over Ka.
Okay, so if you're writing the Ka expression for pH, right, you're writing the equilibrium constant for this reaction. Right? This is the Ka expression. It's the acid dissociation. And so you would write Ka is equal to H plus times P minus over pH. Right? That's the standard Ka expression. It always has the proton and the conjugate base in the numerator and the conjugate acid in the denominator. Right? So if you've got the inverse, if you've got the pH in the numerator, when you take 1 over H plus times P minus over pH, right, the denominator goes up into the numerator, and that becomes pH over H plus times P minus. So if your product is written on, if your acid rather is written on the product side, you're always working with the inverse, right? You've basically multiplied this reaction by -1 to get it from pH on the reactant side to pH on the product side. And if you multiply the reaction by -1, you take the reciprocal of the equilibrium constant. Basically, you take the equilibrium constant to the -1 power. So once you have that, right, you know your overall equilibrium constant, KEQ overall, is equal to Ka for the reactant acid divided by Ka for the product acid. Then we can plug in, because we know that pKa is minus log of Ka, right? Because we know pKa is minus log of Ka, we know that Ka is equal to 10 to the power minus pKa. Does that make sense? It's the inverse operation of the log.
Yeah.
So for Ka of Rh, we can plug in 10 to the minus pKa of Rh. And for Ka of pH, we can plug in 10 to the minus pKa of pH. 1 times 10 to the, put that in there, right? But we know that 10 to the x over 10 to the y is equal to 10 to the x minus y. You're comfortable with that? You know that one?
Yeah.
So basically, I've got 10 to the minus pK of Rh. Minus, right, pKa of pH. Sorry, minus a minus pKa of pH. Okay. Where x is equal to minus pKa of Rh and y is equal to minus pKa of pH. So that's the x, right, minus pK of Rh minus the y minus pK of pH. Those cancel, right? So we end up flipping that to positive, so that K overall, sorry, my H's and my K's look the same, is 10 to the pKa of the product acid minus pKa of the reactant acid. So that's where that equation comes from. If you kind of work with generic values instead of putting in the numbers. And I'll actually post this. I'll add this video as well, might as well, in case anyone else can use it. Does that help some?
Yeah, I really get stuff.
And then it's going to be a matter of, well, did you mess up the knowing the pKa part too?
Yeah, I think so.
Oh, so you've got to learn your pKa's. That part I can't help with. If some things just have to be memorized, and if you refuse to memorize the part that has to be memorized, you're on your own there.
Yeah, I thought I did a good job memorizing, but I think recognizing the students.
Figuring out what kind of hydrogen